Hello everyone and welcome to today's worked exam answer video. Today I'm having a look at an AS organic question relating to alkenes and the electrophilic addition mechanism. So we're having a think about the possibility of us getting two different products of this reaction, which will be structural isomers of each other, and we've got to name and outline a mechanism for the formation of the major product. We've then got to draw the skeletal formula of the minor product, and then we're thinking about adding an excess of the electrophile to have a think about what that would then give us as well. Now, these sorts of questions where we've got an initial alkene that can give us different products based on the fact that we have an asymmetrical alkene and we have a polar electrophile are fairly common. And what you will be asked to do for these questions again is fairly consistent. So naming and outlining a mechanism for the formation of the major product, that will usually be the first question. Drawing the structure of the other product that can be formed, very standard second question. Explaining why we get the different alkene products in different amounts, very common question. And then here we've got the added bonus of a little extra where we've got an excess of the electrophile being added with the limonene, which is the second cyclic alkene that they've given us in this particular question. Now, these alkenes don't look as nice as something like ethene or propene, but it does not change how the mechanism works. Obviously, it looks more daunting and I fully appreciate that, but if you can, try not to be put off by the fact that we've got cyclic alkenes and not just a normal ethene, propene, butanene, that sort of thing, okay? So we've got the 1-methyl cyclohexene, which is this thing here. So the 1 is referring to the position of the methyl group in relation to where the double bond is in the hexene. It's weird to put a number in front of a methyl that is a 1, but we've done it because the double bond, we'd always have that starting on carbon 1, and then we need to show where the methyl group is in relation. We're using HBr, which is a polar electrophile. We're going to form those two structural isomers that I mentioned. We're going to get position isomers because the bromine will be put into two different positions. We're then told that the major product is 1-bromo-1-methyl cyclohexane. So we then know that the major product is going to have the bromine on the same carbon as that methyl group. So we now know what we're aiming to achieve. We're aiming for our major product to put the bromine there. And we then have to name and outline a mechanism for the formation of the major product. Now, it won't always give you a clue as to what the major product is. Here they've very kindly given us the name, but you also need to just be able to look at that as a structure and appreciate the two different carbocations that you can get in this mechanism, and then which product from which of those carbocations would be the major or the minor, which will come in when we explain why we get the products in different amounts. So, outlining the mechanism just means draw it. The name of the mechanism, I've already given that away, is electrophilic addition. Now, in terms of how do I know it's electrophilic addition, we need to know the definition of electrophile. So an electrophile is an electron pair acceptor. In an alkene, we have a double bond, which is a region of high electron density. We're not going to have a nucleophile being able to donate electrons towards a double bond. The double bond is going to want to be attracting something that can accept a pair of electrons, which is an electrophile. In terms of how I know it's addition, once I've drawn the mechanism, you'll be able to see in terms of curly arrows that both parts of the HBr get added onto the final structure. And we can also see that we've kept the methyl group, we've kept the cyclo, we've lost the double bond, but we now have this bromine added on. There's no other products made in this reaction, and if we turn two things, the alkene and the HBr, into one product, then that's addition, always. So even if we haven't learned that this particular mechanism is electrophilic addition, we are able to work it out if we understand how mechanisms work and we know our definitions. So that's another really important point. Okay, so now I've got to try and draw a decent hexagon, which I actually find really hard, despite having numerous years of practice. That is absolutely disgusting, but never mind. So that is 1-methyl cyclohexene, and we've got HBr. So HBr. Now I'm choosing to do it that way so that I can get my curly arrows in a good place. It will always be the delta positive atom of the polar electrophile that will be closest to the double bond, and I'm sure they wouldn't penalise you if you did it the other way, but that is the atom within the electrophile that the electrons in the double bond are going to want to attack. So for me it made sense for me to be able to go right double bond to the hydrogen, and then from the HBr bond to the bromine. Now you don't need to put the partial charges on the H and the Br. I will, so that you know that that's what they are. You can put them on, but you would be penalised if you put them on and got them the wrong way round. So I'm not going to say don't do it, I'm just going to say please take care. Now that is going to give us an intermediate structure. Got to draw another hexagon. Slightly better. My methyl group has not changed. My double bond is not there anymore, and one of those two carbons that was a part of the double bond will have gained the hydrogen. The other will be missing a bond and will have a positive charge, and this intermediate is called a carbocation, cation positive charge on a carbon atom. So if I want to end up with the bromine on the same carbon as the methyl, then the hydrogen's got to have been added there. Now this is a bit weird because this is this is skeletal formula, so I'm not going to draw the hydrogen on there because then that wouldn't be skeletal, but it is there, trust me, it will go there. And then this carbon here would then have a positive charge because we currently haven't added anything onto that carbon, we've just taken away its second bond to this carbon here. So that's our intermediate, and then in comes the bromine that we kind of banished from the electrophile in the first step, and we've got that will have a lone pair of electrons, and that lone pair of electrons on the bromine, which is a bromide ion, my apologies, will then attack the positively charged carbon like that. Now, they've told us what the major product is, so we wouldn't have to draw it. Again, you can draw it, and I'll draw it for your benefit, but if we draw it and we get it wrong, and we accidentally miss off the methyl group, for example, we would then get penalised. So again, you've got to decide whether it's worth it or not. I was really stubborn during my own A-level and didn't like doing a mechanism that then didn't have the final product included. I'm a bit wiser now, I think, and I make the decision not to draw it, but that's what it would look like. So we've got the methyl and the bromine on the same carbon. If they hadn't have said what the major product was, then absolutely we would have to draw it, but they told us what we were working towards here. So that is our mechanism, and that will be our major product. Now, had we have, instead of putting the hydrogen here, had we have put the hydrogen up there, where the methyl group was, then it would be this carbon that would have the positive charge, and then the bromine would attack that carbon, and the bromine would end up in a different place. That's where the minor product comes in, and that's what we've got to draw next, the skeletal formula of the minor product that is made, and we've then got to explain why we get the products formed in different amounts. So why is one of them a major product and why is one of them a minor product? So in terms of drawing the skeletal formula, again, get my hexagon on, get my methyl on, and then the other position that the bromine could be added is the other carbon that was a part of the double bond. So we could get that. Now, when we think about why we get these formed in different quantities, it is down to the type of carbocation intermediate we have. Now, this carbocation that we included in our mechanism, that carbon there is bonded to the methyl carbon, this carbon that's a part of the cyclical ring, and then this carbon here. So that is a tertiary carbocation. Whereas, had we put the hydrogen up there and this carbon here was our carbocation, that carbon would only be bonded to two others, so that would make it a secondary carbocation. And we need to know that tertiary are more stable than secondary, and secondary are more stable than primary. And the more stable carbocation will give us the major product, because the fact it's more stable means it exists for a longer period of time. So there is a greater chance that the bromine will attack the tertiary carbocation, so we get more of that type of product. And the reason why tertiary is more stable than secondary is because the number of carbons influences the stability of this positive charge through something called the positive inductive effect. Now this is a 4-mark question. We're going to get 1 for drawing the structure of the minor product, which means our explanation is going to be worth 3. So we need to give all the bells and whistles in this answer. So let me think about how best to word this. I don't know why I've started with minor, but anyway, so the minor product forms from a less stable secondary carbocation. The major product forms from a more stable tertiary. Carbocation. Now if our explanation was worth 2 points, I would have got the 2 marks for that. 1 for identifying each type of carbocation and 1 for saying which is the more stable of those. So I've already got 2 of the 3 here. The 3rd mark here is for saying why the tertiary is more stable than the secondary. So tertiary carbocation is more stable due, whoops, that's not due to there being the methyl group and that means there are 3 electron releasing alkyl groups. So what those carbon-carbon bonds will do is they will push electrons towards the positive charge, which helps to stabilise it. And in a tertiary carbocation you've got 3 of those because you've got the methyl carbon as well, whereas in the secondary you only have 2 of them. So having a 3rd electron releasing alkyl group is what makes the tertiary more stable. And if you had a primary, you'd only have 1 electron releasing alkyl group, and the more of those you have, the more stable the positive charge is going to be. Let me just add something to the end of here to make sure it's a comparison. So meaning there are 3 electron releasing alkyl groups instead of 2, or just 2. And that will be your 3rd point. So you don't always have to include that. If your explanation is only worth 2 marks, you don't need to. If it's worth 3, then you definitely need to get that in. Now that is known as the positive inductive effect, and you can get a mark for saying that. Yeah, I think this is more, what's the word? Sorry, English let me down again. I think this is more explanatory and is a better answer to give. But positive inductive effect, I'm pretty certain, should get you the mark as well. Okay. Finally, we've now got the limonene at the top, and it says draw the structure of the major product formed when an excess of HBr reacts with the limonene. So with the limonene, the reason why we need an excess is because we've got 2 double bonds, 1 there and 1 there. So they've chosen a second product that has the same thing going on with the top double bond. If we're getting the major product, then the bromine is going to go there. So we now need to decide what the major product's going to be if we want to put a bromine on here. So this carbon will have 2 hydrogens on it. So that carbon, if we put a positive charge on there, would be primary. This carbon here has got that carbon and that carbon. So that would then be secondary. Hang on. No, tertiary. Because we'd have this carbon 1, that carbon 2, and that carbon 3. So yes, so that would be tertiary. So that is again where the bromine is going to go, because the tertiary is more stable than the primary carbocation we would get if the positive charge went there. So that's where my bromines will go. So the excess is because we've got 2 carbon to carbon double bonds. Major product, again, we've got to make sure that we have the more stable carbocations in each case. And it just says draw the structure. Now, it makes sense to just do it skeletally because they've drawn the initial limonene skeletally, but if it just says draw the structure, you could do anything you wanted to, so long as it was accurate. But I'm going to stick with the hexagon, the methyl, the bromine, which was what we said the major product was for the top double bond. Then we've now got an extra bond down here to a carbon, which is now going to have a CH3 coming off it. Just trying to think about how to do this sterically, because I need a CH3, a CH3, and a Br. CH3, CH3, and a Br. So that would be the major product. So as I said at the beginning, if that was with ethene or propene, or if we're thinking about major and minor products, it would need to be with something like butyl-1-ene. We need to have an asymmetrical alkene. But if it was with butyl-1-ene, I think that would look a nicer question. It would be all the same things that we'd be doing, but because we've got hideous looking structure of 1-methyl cyclohexene, I think it might feel a little bit harder. We're also doing our mechanism in skeletal formula as well. So yeah, any queries with that, as always guys, please don't hesitate to get in touch. Hopefully that's been useful, and as always, thank you so much for your support.